Welcome back, Physics 30s, to our next lesson in Chapter 1. This is 1.6, and today we're going to be looking at two-dimensional momentum. Let's consider this collision that could happen on a pool table. So we have this white cue ball that is going to collide with this orange 5 ball, but it's not going to collide directly head-on. It's not going to stay in that same plane. The white ball is going to hit the 5 ball at an angle, and they're both going to bounce off at an angle. So let's take another look at that, and I've drawn these arrows to represent the momentum of each ball. So that first white arrow on the left represents the initial momentum of the cue ball. And after the collision, that top white arrow represents the final momentum of the cue ball, and the bottom orange-red arrow represents the final momentum of the 5 ball. So what we want to consider is if momentum is conserved in this collision. Now, we expect it will be if there are no external forces. And you may be thinking that on a pool table, the balls eventually come to a stop due to friction, so there is significant external force. So for that reason, momentum will not be conserved. However, I've drawn these momentum lines, or these momentum vector arrows, right after the collision. Eventually, those balls will come to a stop, but right after the collision is the time that we're interested in. And right after the collision, they haven't slowed significantly due to friction, so immediately after the collision, we are going to consider friction to be negligible. But it is good to consider that after a long enough time, it will have a significant effect on their momentum. But anyway, back to the diagram, focusing right after the collision, when friction is negligible, let's compare those momentum vectors to see if it's conserved. So I'm going to move the red arrow, or the orange arrow, to that initial momentum arrow of the cue ball, and then I'm going to move the final momentum of the cue ball, add it head to tail like we did with other vectors, and it seems like we have more momentum at the end than we did at the start. So it looks like momentum was not conserved. And that brings us to the focus of this lesson. How are we going to handle momentum when we deal with momentum vectors that are at an angle? And the answer is similar to what we saw before at the start of this unit, was that we're going to treat x and y separately, similar to our other vector diagrams or projectile diagrams. So let's go back to this collision. Again, they collide and bounce off at these angles, but now we're going to look at the x and y components of those final momentum vectors. So I'm going to see the y component with yellow here of the white cue ball, and then the x component like that. Next, let's look at the orange 5 ball. We see there's the x component, and the y component is downwards. Now that we've broken into x and y separately, let's compare x and y momentum separately. Well, at the start, the white cue ball had only momentum in the x direction. So let's compare the initial x momentum to the final x momentum. So I'm going to move those purple arrows over and compare it to my initial momentum in x, and I see that they are equal. So in the x direction, momentum was conserved. Now you might be thinking, okay, well, that works well for x, but what about y? We have still this extra momentum to deal with. And that's true, we still have to look at y, but it's important to remember at this point that momentum is a vector. So direction is important. So that one ball is moving up and the other one is moving down means they're moving in opposite directions, and their momentum would have opposite signs. So now when I compare those two, I'm going to bring that yellow vector up. I see that they're actually the same value or the same length, but in opposite directions. So if the white cue ball is moving upwards with, say, a momentum of 3 Newton seconds, the red ball is moving down at -3 Newton seconds, and it cancels out to 0. And this matches our initial momentum in y. Initially, the cue ball was only traveling in x. There was no y momentum. So I started with no momentum in y, and I finish with no overall momentum in y. So hopefully this shows you that when we look at x and y separately, momentum in x and momentum in y are conserved. So that's the concept for today, that momentum in x and y are conserved separately. I just wrote here that pxi, or the momentum in x initial, is equal to pxf, the momentum in x final. Initial and final are the same. Same for y, the momentum in y initial is the same as the momentum in y final. So looking at just what happens in x, this is similar to just a hit and rebound collision. I have the white ball moving to the left, colliding with the orange 5 ball, and that's my initial momentum. And at the end, if I'm just looking at the x components, the white cue ball is moving slowly, the 5 orange ball is moving quickly, and those purple arrows add up to our initial white arrow. So momentum in x initial is equal to momentum in x final. And if we look in y, this is similar to an explosion that we looked at before in the previous lessons. There's two masses beginning both at rest for our initial momentum, and then at the end, we have them moving in opposite directions with equal momentum, so it still cancels out to zero. Similar to when the astronaut threw the hammer one way and he moved the other. They started stationary, and then at the end, there was positive and negative momentum that canceled each other out to equal a total of zero. So our momentum in y initial is equal to our momentum in y final. Now we're just going to look at an example. This says that a 165 gram pool ball is traveling north at 2.0 meters per second when it collides with a second ball that has the same mass, 165 grams. The second ball travels 1.2 meters per second at an angle of 20 degrees east of north. What is the angle of the initial ball is going to move after the collision? One quick note before we actually solve this, I just made up these numbers of 1.2 meters per second and 20 degrees. That may not occur in real life, but this still will show us how to solve questions like this that you'll see on practice questions and tests. Okay, so let's first put in the information that I know. I know each ball is 0.165 kilograms. I know that the cue ball is initially moving at 2.0 meters per second. And I know that afterwards, this red or orange ball is moving at 20 degrees at a speed of 1.2 meters per second. So I think a good first step in any time you see an angled vector in pretty much any question in physics is to find those components. So I'm going to try and find the y component and the x component of this vector here. So for finding the x component going this way, I'm going to use sine 20 degrees multiplied by that 1.2 meters per second. And I'm getting a number of 0.4104 meters per second. And then to solve for the y component, I'm just going to write it over here. I'm going to use cos 20 of that same 1.2 meters per second. And I'm getting a value there of 1.1276 meters per second. Okay, so next I'm going to look at x and y separately. So in the x plane or the x direction, momentum has to be conserved. So my momentum initial has to equal my momentum final. At the start, there's actually no momentum in the x direction. The white cue ball is just moving in y. So initially, there's no momentum in x. But at the end, both the 5 ball and the cue ball have momentum. So I'm going to put mv plus mv. I do know information about the 5 ball, so I'm going to start with that and say that its mass, as mentioned in the questions, is the same, 0.165 kilograms, times by its velocity in x, which is 0.4104. Let's consider this direction to the right to be positive and going to the left to be negative. So I'll put a little negative there and a plus over there. Now considering the cue ball, I'm going to say plus the mass. We do know that is 0.165 kilograms, and the velocity I don't know. The next step you could solve for this part, but I'm actually just going to subtract that over on the other side. So 0 minus that will give me negative 0.165 kilograms times 0.4104 is equal to 0.165 kilograms times velocity. And the reason I did that is we can see that because we have the same mass on both sides, we can actually cancel this 0.165 from each side and realize that the velocity I get is negative 0.4104 for my velocity, which makes sense because if they're the same mass and momentum was 0 at the start, it has to be 0 at the end. If it's positive 0.4104 one way, it has to be negative 0.104 the other way. And if they're the same mass, their velocity should be the same. So that's velocity in x, but now we have to look at the velocity in y. I'm just going to switch colors to orange here. It doesn't correlate with the diagram, but just to show it kind of as separate, I'm going to put in y that momentum also has to be conserved. Pi is equal to Pf. At the start, we have momentum in the white cue ball. So I'm going to put mv, but there is no momentum in the 5 ball. Afterwards, there's momentum in both, mv plus mv. Now this won't happen in all examples, but this one's really nice because the mass of both balls are 0.165 kilograms. So if the mass is the same in all terms here, I'm just gonna cancel all of them out. Again, that won't happen in every question. If there are different masses colliding, you can't do that, but in this case, all the masses are the same. So I'm gonna say that we start with a velocity of 2.0 meters per second. Then I know that the 5 ball in y has a velocity of 1.1276 plus v. That's going to be the leftover velocity for the white ball. So now I'm just going to minus the 1.1276 minus 1.1276, and I'm getting a number there of 0.8724 meters per second for the white ball's velocity in y. Just to clear up space, I'm going to wipe out all that work except for those 2 final numbers so we can get our final answer for an angle. So now I'll put those 2 numbers together, my y of 0.8724 meters per second, and then my x of negative 0.4104. Then I just need to find the angle here by using inverse tan. So tan, can't see it there, tan negative 1 of my 0.4104 over the 0.8724 to get my angle, because that's all it asked for in the question, was just the angle initially after the collision. And that gives me a number of about, rounding to 25 degrees for my final answer. Okay, so not too much notes on that, but this can apply to lots of different scenarios. And again, those skills of breaking into X and Y components and handling conservation momentum will be key for solving any of these problems. And that's it for today's lesson. Thank you so much for watching. Try those practice questions, and I will see you in the next video.